Now we can augment our simple regression model with other x variables, and we can then start with regression multiple, and we use the linear model, and price is still our y variable. And if we want to test all of the other variables in our data frame versus price, then we just type this dot and data equals data as usual. So then we can just run this. We see that we have gotten a data structure with regression multiple, which contains the coefficients, the residuals, the effects, and so on. And if we look at the summary of this variable, like so, then we see that there are some variables which have a high degree of significance, whereas others do not have that strong significance, and others, like floor, does not contain much information at all. So in this case, it seems like the difference between the simple regression model from the last video and this model is that the intercept is now not statistically significantly different from 0, but other factors like whether or not the city's Oslo has a more profound influence on the price. And we saw that in the residual plot when we plotted the residuals versus the square meters. We saw that the first observations of our data, the prices were higher than the model predicted, whereas for the last part of our data, the prices predicted by the model was too high. And this coincided with the structure of the data, where the apartments from Oslo were at the start and the apartments from Trondheim were at the end. So here we have seen that if the apartment is in Oslo, the difference is significant, statistically significant, and you would then expect an apartment in Oslo to cost 2.2 million more than in Trondheim. And we can also see that now the square meters are significant and much higher than in the simple regression model. So now it's 59,218 kroners per square meter, or per extra square meter. And we also see that the adjusted R squared is a lot higher, and we can compare this to the linear model where we had, or the simple regression model where we had the same price y variable. And the F statistic now says that, well, statistically speaking, the R squared value here is different from 0, which means that at least one of these slopes here, not the intercept, but slopes, is different from 0, statistically speaking. Okay, so what can we do with this model? Well, we can predict prices given that we have these informations. The most important ones would be square meters, bathrooms, and whether or not the apartment is in Oslo. What we can do is we can change the model. This is not always recommended, I have to say, but for simplicity's sake, we say that for this case, we only keep the variables which are different from 0. So here we can estimate price, and it's dependent on square meters plus, let's see, bathrooms plus Oslo. And the data is still our true and trusted data frame. We can look at the regression, and here we see that, well, with this reduced model, we actually get a significant intercept, a significant square meters, and significant bathrooms, and significant difference between Oslo and Trondheim. Which means that the other variables here, they probably added some noise to the model. So it was good riddance. And now we can use this model to predict houses or predict apartment prices in Oslo and in Trondheim. And what we can do then is that we just use the model again, like we did in the previous video. For example, if we have an apartment in Trondheim, we have the intercept plus, for example, 50 square meters times 6,578 plus the number of bathrooms, maybe one bathroom for a 50 square meter apartment, times the price here, which is incredibly low. So maybe this is a result of multicollinearity or a lack of data points, and 0 times the Oslo value here, because our apartment is in Trondheim and not Oslo. If it had been in Oslo, then this would be 1. So now we have an estimate of this apartment in Trondheim, which is 2.96 million kroners. So this is how we actually can use the output from this model to make a prediction.